Hi there, Year Nines. This is a video just to give you a bit of a guidance of what the Loot Boxes Exercise 9F activity was about. So we talked about experimental probability versus theoretical probability in class. And if you missed that, essentially, for example, I'm just going to do a quick one here. When you flip a coin, you would say that the probability of getting tails, for example, is half. So this is called theoretical, okay? But when you actually do the experiment, right, so the experiment, you'll find that if I asked you to flip it 10 times, if you flip the coin 10 times, right, it's not really true that everyone in our class will actually get 5 tails because it's 50%, right? It's not true that you're going to get 5 tails and then 5 heads. So the probability could end up being one of you might actually get 7 tails and then 3 heads, which means that the probability is 70% versus 30%. While someone else might actually get, they could get 8 tails and then 2 heads. So that becomes 80% and then 20%. So this is called experimental probability. So this is the real life experiment that you test, and then you're comparing it with the theoretical probability. So in this activity here, what are we doing? Well, we've got a task where you're imagining that you are wanting to collect a set of items when you play a game, right? The task is to determine how many of these loot boxes, so when you grab these boxes, how many of them do we need to open to get the full set? So we assume that each loot box is independent of any other box. And what that means is that when you open one, it doesn't affect the chances of the next one you open. So here, and all of the boxes have an equal probability. So that's probably key for the first one. All right. Now, imagine this. If you had a 5-item set it's like, imagine you're playing a game that you can get legendary items, like you can get a helm, you can get an armor, you can get a bracelet. So 5 items. So that's 1, 2, 3, 4. Let's say you get shoes. What else am I missing here? And let's just say necklace. Okay. So there are 5 legendary items, and this is called a perfect set, right? And what they're saying is that there are no distractor items. So it means that these are all legendary. So in this box that you're about to open up, in this loot box, when you open up this box, it only will give you one of these legendary item list. Okay? Because it doesn't have any distractor items, like common items. You know how when you open up boxes, you get common items versus legendary items, or like rare items and then super rare. Well, imagine legendary item in this box, you're always going to get a legendary item. You're guaranteed you're going to get one. Okay? So they're saying there's no distractor items, and they want to know what is the probability of getting the 5-item set. So you get the full set if, for whatever reason, when you first log in, someone was nice enough and they bought you 5 of these legendary boxes. You've got 5 boxes. The question is, what's the probability that when you open them, each one gives you a unique new item? So you actually get the helm, you get the armor, you get the bracelet, you get the shoes, and then you get the necklace, all in this 5 boxes in one go. What's the chances of that happening is what they're asking. Okay, so I want you to pause the video and have a think. See if you can answer that. All right, assuming you had a thought. So here, what's the chances? Well, first thing, when you open up this loot box, right, you already know you're going to be guaranteed one of these items. You're going to get a helm, armor, bracelet, shoes, or necklace. So you have a 1 in 5 chance because you're only getting one item, right? So you get a 1 in 5, 5 options, you get one of them. So helm, armor, bracelet, shoes, or necklace. You're going to get one of them. So now that would be a 1 in 5 chance when you open up the first one. When you open up the second one, I know that you could get a replica, right? But because this question is actually asking what's the chances of you getting a 5-item set, well, it means that each one has to be different. So if you've got the helm on the first go, right? Well, now you only have 4 options left, right? You only got the armor, bracelet, shoes, and necklace for you to get a full set out of these 5 boxes that you open. So really, there's only 4 items left, and you can only get one of them out of that box in the second box. So when you open up the second box, you get another item, and there's only 4 things that you can have left. to reach a perfect set, right? And then same thing for the next one. You only now have, let's say you got the armor on the second go. Then the third one, you might get the bracelet. So out of 3, you only have 1 to pick from. And then out of 2, you got 1 left. And really, after you get all of the other ones, there's only 1 left to pick. And you get to pick up the last item in the last box. So this is the chance if you were to get a perfect go. If those 5 boxes that you got to get a perfect set, this is your chances. So 1 times 1 times 1 times 1, we know that's 1. And 5 times 4 is 20. 20 times 3 times 2 is 6. So 20 times 6 is 120. So this is your theoretical probability. You have a 1 in 120 chance to get a perfect set with just 5 boxes. Okay, so with just 5 boxes, if you were to open them, there's a 1 in 120 chance. Now that's the theoretical probability, right? So part B, they say, why do the denominators decrease after each box? Well, you can explain it now because I've explained it in the sense that because after you choose 1 item, there's only another 1 less item to get your full set. Okay, so after choosing or getting an item, there's now 1 less to get the full set. Okay, that's the explanation. You can write it in any other way, right? So hopefully you're starting to get the feel of it. You got these 5 boxes, and we've now got the theoretical probability here. So that's the theory. Now moving on to this part here, C. Some of you asked me last session, and I wasn't sure until I actually did this worksheet. Now I understand what it's asking. There's no right or wrong answer here. What they wanted you to do was, you know the theory now. So you know theoretically you got a 1 in 120. They're asking, well, estimate how many boxes do you think you would need to open on average to get the complete set? So right now, clearly the chances of you getting 5 boxes, if you bought 5 boxes, your chances are pretty low that you're going to get a perfect set on the first go. Let's say you had infinite money and you can buy as many boxes as you want. How many do you think you would need to guarantee that you would definitely get 1 perfect set? That's all it is. You have to do just a guess. So here you can guess anything. Okay, you can guess, since this is 1 out of 120, you can guess it takes 121 boxes. Okay? Doesn't matter. This is just your hypothetical guess. Or you might say, well, if it's 5, maybe you only get 6 boxes. It's up to you. What do you realistically think? This exercise is to get you to think, okay, we've got the theory. Well, what about realistically? What are we likely to get? Okay? So here in the next example or next question, now that you made your guess, they want you to go to Google and you go to Giga Calculator, random number generator, type that in. And the website looks like this. Okay, so it'll come up like this if you Google it. And then here, you can then type in the range. Now, we know that if we listed the items, the 5 legendary items that we want, let's just call the helm number 1, call the armor number 2, call the bracelet number 3, call the shoes number 4, and number 5 is the necklace. Then you limit it from item 1 to item 5. Okay, and how many numbers do you want? So this is how many boxes do you want to try? So in this example, they're going to get you 13 random boxes. So imagine this was your box number 1. You open it. Which one are you going to get? Are you going to get item number 1, item number 2, item number 3? We don't know. So initially, the first example was 5 boxes only. Well, now you've got 13 boxes, and they want you to simulate how long before you actually get a full set. So if you're confused, let's do this together. So I'm going to go to a website. I'm going to type Giga Calculator Random Number Generator. I go to this one, first link. And then here, so I want the range. So items can only be 1 to 5, right? Because there's only 5 items that I'm looking for. Now, if I put 13, because I'm going to buy 13 boxes, here make sure to click no repeats because we do want them to have repeats. You can have multiple helms and multiple bracelets. You can get duplicates, right? So here I'm going to say, give me any 13 random boxes. Imagine I open up 13 boxes right now, and what do I get? And this is what I get. So this is my result. So I'm going to copy that for the first trial. I'm just going to delete this one. So, because this was me trying it out before. Whoops. Let me just delete these other trials. Delete. delete, delete. All right, so the first trial that I just did, so my first box, I get number 3. 3 was my bracelet, I think it was. So I got a bracelet on the first box. Second one, I got a shoe. Then I got a helm. So that's pretty good. I got 3 out of the 5 items. They're all different. Then I got a helm again. Then I got a helm again. Then I got 4, which is a shoe again. So I still need a armor to make a full set. And I also need, what else do I need? I need a necklace. So I still haven't got a necklace or an armor. So you can see that, how many did I have to go? 2 was I think that was the armor. So I finally got armor. I got 1 more item to get a perfect set. And I need number 5. And you can see this is another helm. And then I finally got my 5. So what they wanted you to do here is tick it off as you look at the numbers. When do you actually get your full set? So clearly, I got my full set after how many boxes? How many boxes did I have to open? We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I had to open up 10 boxes. So if you fill it out, it was 3, 4, 1, 1, 4, 1, 2, 1, 5. I'm missing something, aren't I? Oh, there's 3 ones. Whoops. 3 ones, 4, 1, 2, 1, 5. So that clearly took me 10 tries to get 1 full set. And then you do it again. Okay, so you do it again. So in this case here, how long did it take you to get your full set? Well, the probability was clearly it took you 10 trials to get. Whereas up here, we were guessing either 121 boxes or you're guessing 6 boxes. It's up to you what your guess was. But that's where E, they were saying, well, calculate on average if after you do simulation number 2, simulation number 3, how many trials? So let's say the next trial I got 15. Let's actually do a proper one. So I'm going to do the second one now. So simulation number 2, let's do it again. Get random numbers. Here's my new set. Here's my new set of numbers. Okay, and let's just put it down here. Let's see how long before I get a full set. So I got 1, good. I got 1 of the 1s. I got a 3. I got a 4. I got a 5, and I need a 2, and it looks like I never got a full set. So this one doesn't work. It means I have to generate it again. So let's generate it again. And let's see if this gives you a full set. So I'll do it again. Here we go. I got 1 item. 1 item. Good. 5. 1, 2. Yeah, I need a 2 and I need a 3. Is that everything? 1, 2, 3, 4, 5. Yeah, that's 5 items. So I got a full set after how long? And again, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 boxes in order to get a full set. Remember, the numbers have an equal chance of coming up. So this is simulating it, isn't it? So here I needed 11 trials. Imagine if I did the next one and I needed 16 trials as an example. Then when they say on average, how many tries did it take to get the set? Well, based on our experimental data, I had 10 on the first trial or simulation, and then 11 on the second simulation, and then the third was 16. Then on average, you can work out your average now. So average is what? 10 plus 11 plus 16. Where's my calculator? 10 plus 11 plus 16, and then divided by 3, is, it should be this one, is 12.33. So what does that mean? Was it more than you thought? This is where you make a comment. So 12.33, it means that I need about 12 boxes or more to get a full set. Was that what you thought? Meaning comparing to what you said in part C, was that what you thought? Did you think it was less or was it more? And that's essentially this first part of the exercise. Okay, so hopefully I've given you a bit of guidance there on what the problem is, because then when you do number 2, the only thing they've changed now is instead of opening up a box and you're guaranteed you're going to get one of the 5 legendary items, 1, 2, 3, 4, 5, they're saying that there are 5 distractor or junk items. So imagine that you get another 5, 1, 2, 3, 4, 5, but these are the common items. So common 1, common 2, common 3, common 4, common 5. So now there's a total of 10 items. How does that change things? So again, work out the theoretical probability, estimate what you think, how long it takes on average, and then do a simulation. But this time you've got 16 box, or actually generate 25 random numbers. So I think there was not enough here, but if you generate 25 random numbers, how long does it take before you get a full set? How long does it take? Do at least 3 simulations, get the average for it, and then get the average for any duplicates. So how many average duplicates did you get in your trials? And then F, what if it did cost you $2 to buy these loot boxes each time? Okay, let's say you bought 13 of these boxes through your app. So you buy 13 of these boxes, and then it cost you however amount, right? And let's say you got half of it. So they're saying, what if you had half the set? Okay, so out of the 1, 2, 3, 4, 5, let's say they give you 5. You got half the set. You only need 2 more. And let's say you spent, I don't know, $100 on this game, on your mobile game. Do you think that if you spend another $100, you are guaranteed that you're going to get a full set? And with hopefully with all your data and experiments so far, you can come to some sort of conclusion. They just want you to explain and reason why it can be misleading in terms of probability. It may not be as easy as you think. And that's a bit of a deeper question, but it's just for you to explore. And then part 3 is similar. Okay, so part 3, you've got 5 items in a loot box, 5 distractor items, but now the 5 items in the set are 5 times rarer. So they're not equal chance. So you know how I drew a box before? When you open up a loot box, it's not guaranteed that they all have an equal chance of getting it. What if it was rarer to get the legendary items? So 1, 2, 3, 4, 5, and then you've got common 1, common 2, common 3, common 4, common 5. What if you have a higher chance of getting a common and it's much rarer to get those legendary items? Then how does that change your theoretical probability? Okay, so we can simulate this by making the numbers 1 to 5 the set items, and then the numbers 6 to, in our case, it would be 6 to 10. But this is where I want you to think, is it actually 6 to 10? Because it feels like 6 to 10. Because if you do 1, 2, 3, 4, 5, and then the common items was 6, 7, 8, 9, 10, right? There's 5 common items, and then there's also 5 rare items, yeah? I want you to think for a moment, the chances of getting this is a 1 in 10, 1 in 10, 1 in 10, right? But if you double this, if you said common items was 6 to, say, 11, 12, 13, 14, 15, so that's another 5. So now there's 10 items here. So the chance of you getting a common item now at this 6 is a 1 in... Actually, yeah, sorry, it makes this rarer. What am I doing? So this now is a 1 in 15, but then the common items, you get a 1 in 5. Sorry, I'm mixing it all up. Let me just fix that. The ratio is the rare items is 5, and now the ratio for the common items is 10. So it's a 1 to 2 ratio, which basically means that if you do it this way, if you did 6 to 15, then common items have double the chances of occurring, whereas this one has half a chance. Or if you think of it, a 1 to 2 ratio essentially means that 1 part is rare and 2 parts is common. So you got a third of a chance of getting a rare, and you got 2/3 of a chance to get common items. So this makes rare items harder to get. Get me? So you can play around with ratios. This I'm obviously guiding you a bit here, but I wanted you to think, well, how can you make rare items really rare? Okay, and how many common items must you add? You can play around with this ratio and can make it much rarer. So if you tried to change the ratio, say, to 1 to a 9-part ratio, then you've got now a 1 in 10 chance of getting, so that's 0.1 chance or 10% chance of getting a rare item, whereas a common item, now you have a 90% chance of getting a common item. So it just means that as long as you make the ratio 1 to 9, well, what numbers do you have to do? 6 to what? So it's up to you how you want to do that. I think I guided a bit there, maybe too much, but that's what makes question 3 really fun to do. And then you do the simulation again, this time with 32 random numbers, and then you do the whole questioning again and see, has things changed when you change the probability of getting rare items versus common items? Okay, so hopefully this diagram here helps you figure out how to set up to change the ratio using the number generator. But I hope that makes sense of what I was doing there. I know there was a bit of maths there, but hopefully it makes sense to you that clearly there's 10 common numbers or common items versus only 5 common items. Then that's 5 to 10 is the same thing as a 1 to 2 ratio. And then when you say 1 to 2, well, that's 1 part rare, 2 parts common. That means in total there are 3 parts there. So 2 out of 3 is common, and then 1/3 is rare. So then if you did the same thing for this one, then you can then figure out how many numbers you should have. Okay? I think that should guide you enough to do this. And I think that's all I want you to have an attempt, because it gets you to actually apply experimental probability in exercise 9F. And that's the idea, just to get you to think about theoretical versus experimental. And this is relating to loot boxes and games, and you might feel a bit of relevance to it. And if you want to push yourself, you can also start to look at extension, but you don't really need to. It's only if you feel like it. You got this week to do this exercise, and then you'll upload that, and that's it for this term. So exercise 9F, the loot box activity, is the last one to do. You'll then prepare yourself for the mastery task next week, and then start preparing for exams. Okay? Thanks, team, for watching.